now looking at stability. Stability is all about keeping the line of gravity with the centre of mass all in line. So the centre of mass is constantly changing, especially in a game like basketball where the player is always moving. But stability is very important for a defender, for example, as they need to be able to have good stability and balance to be able to react quickly to an attacker trying to get past them. And for stability, the line of gravity needs to be within the base of support for balance. So looking at this diagram here, their line of gravity is looking at a centre of mass, which would be here. Their line of gravity is directly perpendicular to that, and as they shift the weight around, their centre of mass shifts as well. So that means their line of gravity is constantly moving. And with a look at this diagram here, since they're leaning, their line of gravity is getting outside of their base of support, and when that happens, that means that they will fall over. So to increase stability, you'd want a lower centre of mass and a wider base of support, just like this performer here is doing. As they've squatted down, their centre of mass has gone from here to all the way down here, and then their legs are more shoulder width apart rather than next to each other, increasing their base of support. And this position here, this then gives them the most stability possible, meaning that they would quickly be able to take the ball back from an attacker. And then obviously if their base of support is reduced, so if they're standing on one leg, for example, and their centre of mass is very high up, that means they're going to have a very little stability. So if an attacker was to run into them, for example, they would more likely be able to fall over, meaning that the attacker would easily be able to get past them with a low amount of stability. Linear motion now. So linear motion is moving in one single plane of motion, and there's two different components when it comes to linear motion. You have scalar components and vector components. So scalars and vectors are both units of measurements, whereas however a scalar only contains a magnitude, and a vector contains both magnitude and direction. So, for example, a scalar would be mass or speed, as it's not necessarily relevant to a point or direction of speed. However, a vector looks at weight, velocity, and acceleration. For example, they're just a few. And velocity, for example, that is how fast a body is traveling from a set point, so in a certain direction. And weight takes into account gravity, which obviously has a direction as well. So weight would then be a vector, as it takes into account of both the magnitude and direction. So two differences here. So you have distance and displacement. So distance would be the scalar quantity, as it doesn't take into account a set point. So a distance covered in a basketball match would just be how much they've run overall, as they're constantly going backwards and forwards in the court during a match. So their distance would be quite great compared to their displacement, which is how far an object has travelled from a set point. So saying if a set point was in the centre here, the max displacement they could have would be on the other end of the court. So over a period of time, over a game of basketball, their displacement would be where they finish and where they end up. as it would constantly be their distance compared to a fixed point. So there'd be a great difference between distance and displacement over a course of a game of basketball. Speed and velocity now, they both differ as well. So speed is relative to the distance, and then velocity is relative to the displacement of a body or an object. And as this is relative to distance, the speed is then a scalar quantity, and as velocity is relevant to displacement vector, that is also a vector quantity. And you can calculate speed by distance divided by time, and you can calculate, similarly, you can calculate velocity by velocity equaling displacement over time. So in a game of basketball, analysing this, you would most likely analyse their speed, as they would be covering a greater distance. However, you can use velocity for a more specific time of game. So if they run from the key in basketball to the other ends and the attacking end in a counter attack, for example, there it will be a set displacement from one point to another, so you can find out their velocity in that set period of time, which would be much more accurate compared to their speed. And then in this, there's two types of you can form two types of graphs that differ from each other. So a distance time graph takes into account distance on the y-axis and time on the x-axis. So in a distance time graph, an acceleration would be a curve, and a straight line with a positive gradient. That would be they're traveling at a constant speed, but they're moving. And then obviously if the gradient is lower compared, like for example this green line to the red line, the red line would be moving slower as it has a lower gradient. If it has no gradient, so it's a straight line, this means that the body or the person is stationary. And then obviously if it's a negative gradient, that means they are returning to the start. Looking at a velocity time graph, however, the gradient shows the acceleration. So whereas this was a curve in distance time graph and the straight line showed a steady speed, this here shows a straight line showing acceleration. So as time goes on, their velocity is increasing, meaning they are accelerating, because acceleration can be calculated by the difference in speed over time. So it will be difference from this point to this point divided by their time. Therefore, if it's flat with no gradient, that means it's a constant speed. And then obviously a negative gradient shows a deceleration as they're slowing down. So then when velocity is at zero, that means they're obviously not moving. So that line would be straight at zero at any point to show that they're not moving in this graph. It's also important to note that acceleration is relative to the rate of change in velocity. And so change in direction in basketball, to run back to defend, would be a change in acceleration, but also would be negative acceleration, as velocity was a vector quantity. So looks at from a set point. So if they change direction, then acceleration would be negative as they go in the opposite direction, but they're also increasing in speed as well. For our investigation, the method we should use, so the vertical jump test first. So this was to measure their power in their legs, as this is very important in basketball. You got, for example, the tip off to start with. you want to be able to jump higher than your opposition, so you want the greater amount of power to do that. So an ideal way of doing this would be using a force plate to measure ground reaction force, as this uses, as looking back to the third law of motion, a force applied using equal and opposite reaction. Therefore, the ground reaction force would be equal to the force applied by the performer. But first, this needs to be calibrated to get accurate results. So you would use a known mass to be able to set the force plate at 0 to then be able to get accurate results. Because without accurate results, you wouldn't be able to properly analyse those results and know where the performer would need to work on or improve to be able to develop their power. So this would be an example of a performer using a force plate. So they would stand on this force plate and just simply do a vertical jump. And the force plate records thousands of measurements of force per second. So this creates incredibly accurate and detailed data. And this graph here would be an example of the data produced if a performer was to take that vertical jump test. So they would stand on the plate first to create this straight line of normal data. They would then squat down, which would then cause a decrease in force, and then they would apply their muscles to generate force to jump up, which will cause a spike in force as they leave the ground. And then as they aren't touching the force plate anymore, the graph will show 0, as obviously there's no force being applied. And then when they touch back down to the ground, the force plate would spike, and then the test would be finished after that. Since we don't have access to this obviously advanced equipment, we simply used a simpler method of calculating the vertical jump test to show that, to work out how high the performer can jump, and then calculating power from that later on. Secondly, to measure speed and acceleration, we use a 20-meter sprint test. And also an ideal method of this would be using timing gates to measure speed, and then therefore from the speed be able to calculate acceleration using the change in speed over time formula. And these timing gates have lasers that cut across them, so when they get cut by the or interfered by the performer running through them, it will then clock what time they ran through that. So this removes the possibility of human error, as this would be incredibly accurate, probably to the 100th to a second or something like that. This also removes perspective error, which is part of the human error, as if they were running 20 meters, a person would have to stand at a set point and see them run through these different areas in at different angles, meaning by the time they press their stopwatch, the performer wouldn't actually be at the through the gate at that time. So using this, it's all about using accurate and precise data.